In the first lesson in this unit on absolute value, we looked at absolute value functions. We just looked at what an absolute value is. We looked at how its graph is created and things of that nature. So what we're going to talk about next is we're actually going to talk about solving absolute value equations. And we can do that in a couple of different ways. The first way we're going to look at is solving them graphically using our graphing calculator. And a couple of things you're going to need to know how to do is to actually type in an equation in your calculator and then how to come up with a solution. So the first equation that we're going to start with is the absolute value of 2x plus 3 equals 8. So basically what we're going to do is we're going to graph the absolute value of 2x plus 3 in y1, and then in y2 we're going to graph just 8. And we're going to find the point of intersection of those graphs. Now, if we go into our calculator, into y1, your calculator does not actually have absolute value bars. So when we go to type in something like the absolute value of 2x plus 3, what you need to do is you need to press the math key and you need to press the right arrow and go over to number. And the very first command that you're going to see at number 1 here is ABS, and that's short for absolute value. So we're going to hit enter, and we want to take the absolute value of 2x plus 3. Don't forget to close the brackets. And we want to know where 8 intersects that. Now, if you look at our grid over here, it's a normal kind of a window. X goes from negative 10 to 10 and Y goes from negative 10 to 10. So we're just going to hit zoom 6. We're going to look at our graph. So basically what our graph looks like our graph has an x-intercept at negative 1.5, and we have a horizontal line that crosses our graph at 8. So if we make a quick sketch of that particular graph, so negative 1.5 is about here. And so our graph kind of goes like this. And then at 8, we have a horizontal line. And we're actually going to look for these 2 points of intersection on our graph here. So if you remember from previous lessons, how we find the points of intersection is we press second function and trace. And then we go down to number 5 for intersect. And it's going to ask us for the first curve. And right now you're going to notice that our cursor's blinking here on the right side. I'm going to use the left arrow, and I'm actually going to scroll over to the left. I'm actually going to scroll so I'm just above that point of intersection. I'm going to hit enter. It asks for the second curve. Well, it should have jumped down to our line at 8. And then it asks for guess. And yeah, I don't want it to guess. I would have guessed a long time ago if I wanted to. And it tells us that the first value or first solution to this equation has an x value of negative 5.5. So I'm just going to write that down. X equals negative 5.5. And we're going to go back and we're going to find our second point of intersection, second function trace, and we're going to go down to number 5 for intersect. And this time I'm going to scroll over to the right until I get close to our point of intersection and hit enter. Jumps to the line, hit enter, and when it says guess, hit enter. And our other point of intersection has an x value of 2.5. Now, just like when we solve things algebraically, we have to check these solutions in our original equation and make sure they work. So we have to plug negative 5.5 in here. Well, negative 5.5 times 2 is negative 11. Negative 11 plus 3 is going to give us negative 8. And the absolute value of negative 8 is positive 8. So that checks out. Here, if we take 2.5 and plug it in, well, 2.5 times 2 is 5. 5 plus 3 is 8, and the absolute value of 8. So both of these do in fact work. We confirm that yes, the solutions we got graphically are actually the same solutions we would get if we plugged it into our original equation. We're going to try one more question solved graphically. We're going to try this example here that's the absolute value of 3 plus x and 2x plus 1. So in y1 on our calculator, we're going to put the absolute value of 3 plus x, and in y2, we're going to put 2x plus 1. So we're going to go back into our calculator. We're going to clear out everything that's there. And I'm going to go back to math. I'm going to go over to number, choose absolute. I want the absolute value of 3 plus x. And in the second equation, we want 2x plus 1. And we're going to hit graph. What we notice here is that we actually only have one point of intersection in this case. This particular equation, 2x plus 1, is a line, so we're only going to get one point of intersection between our v-shaped absolute value graph and our line. So we're going to go second function trace. We're going to choose number 5. We are kind of close to our point of intersection here, so I'm just going to hit enter. It's going to jump to my line, and I'm going to keep hitting enter, and it says the x value at this point of intersection, I have an x value of 2. And if we try it up here, 3 plus 2 is 5, 2 times 2 is 4, and 4 plus 1 is 5. So it does check out and it does work. So we've done a couple of examples of solving things graphically. If we make a quick sketch of what this last one looked like, it kind of looked like this. We had a point of intersection here at 2. Now we're going to be moving on to solving our equations algebraically. How could we solve an equation just like this one here without graphing it, but actually come up with an algebraic solution? We're going to now move on and we're going to solve some equations algebraically. I'm going to show you a couple different methods for solving equations algebraically. You can decide which method you like better and go with that particular method. I'll tell you which method I like better once we get to that point, and we'll go on from there. So if we look at this first equation here, absolute value of 2x plus 3 equals 8. The first thing we have to do is we have to take that 2x plus 3 that's inside the absolute value bars, and we need to make it equal to 0, and we need to solve it for x. And we get x to be negative 3 halves. So what we do is we draw a number line, and we put negative 3 halves on the number line. And we have two possible solutions for this situation. We have a situation where x can be less than negative 3 halves, and we have a situation where x can be greater than or equal to negative 3 halves. Remember from our first lesson, when we expressed absolute value function in terms of a piecewise function, we had to look at the two domains, the left and the right domain, that we had to use. Now, if you also remember, there's two possibilities that we can have for this absolute value situation. The value inside this absolute value bar could be positive, or the value inside the absolute value bar could be negative. So if you look at this situation, then we take a look at what's inside the absolute value bars, and we state that that value could be negative. We put a negative in front of it, and we put it in brackets because that negative has to be applied to everything. The right-hand part of our subdomain is where everything inside the absolute value bars could be positive. So it doesn't change, it just stays as positive. Now if we expand this, we multiply the negative 1 through, we get negative 2x minus 3 equals 8. If we add 3 to each side, we get negative 2x equals 11. And if we divide by negative 2, we get negative 11 halves. That's one of the possible solutions. Now it says, is this solution in the subdomain? Is this solution negative 11 halves, is it less than negative 3 halves? Yes, it is. So that means it works. If we solve this, we subtract 3 from each side and we get 2x equals 5, and we get x equals 5 halves when we finish. Is 5 halves greater than or equal to 3 halves? Yes, it is. So we have two solutions to this equation, negative 11 halves and 5 halves. Now that's one way to solve this question, is by looking at these domains and setting up the solution. Now we're going to look at the second question here in a slightly different way. What we're going to look at is we're going to break this equation into two parts. And all we're going to do, we're not going to worry about this subdomain and the number line. What we're going to say is, well, you know, this expression inside the absolute value bars could be negative, and this expression inside the absolute value bars could be positive. So we have to look at both situations, and we're going to solve both situations. This is going to give us negative 3 minus x equals 2x plus 1, and this gives us 3 plus x equals 2x plus 1. If we finish solving the left-hand side, I'm going to add x to the other side and get negative 3 equals 3x plus 1. I'm going to subtract 1 from negative 3 and get negative 4 equals 3x. So I get negative 4/3 equals x. And I'm just going to leave that solution for now. If we look at this right-hand side, if I subtract x from each side, I get 3 equals x plus 1. And if I subtract 1 from each side, I get x to be 2. So I have two possible answers that work here. Well, what I have to do is I have to check these answers back in the original situation and see, do these answers work? So we're going to start with 2. 3 plus 2 is 5. 2 times 2 plus 1 is 5. So 5 equals 5. Or if I show that check, because some of you might be going, oh, I can't handle that. What I'm going to do is I'm going to replace x with 2. So I get 3 plus 2 equals 2 times 2 plus 1. Everywhere there's an x, I put in a 2. Well, 3 plus 2 is 5, and the absolute value of 5 is 5. 2 times 2 is 4. 4 plus 1 is 5. So this checks out. X equals 2 is a solution. Now let's check negative 4 over 3, which is negative 1.3 repeating. So I'm going to start with my original function, and I'm going to plug this in. I'm going to get 3 plus negative 4/3, and I'm going to get 2 times negative 4/3 plus 1. Well, this is 3 minus 1.3 repeating, or 1.6 repeating, which is just 1.6 if I expand it. This is going to give us negative 8/3 plus 1. Negative 8/3 is negative 2.6 repeating plus 1, which gives us negative 1.6 repeating. Well, 1.6 repeating does not equal negative 1.6, so negative 4/3 is not a solution. So the only solution to this problem is 2. Now I've showed you two methods. I've showed you how to do this subdomain, and I've showed you how to just make one of these negative and one of them positive, solve it, and check your answer. I prefer this second method because sometimes you can get confused with this subdomain and this number line, and that can cause you some problems. In this method I've shown you in the second case, it's not really, there's nothing really to mess up. You just make the absolute, what's in the absolute value bars negative, and you make it positive, you solve for x, you check it, away you go. So let's look at one last example. We're going to go to the last page, and we're going to look at this example, x squared minus 9 equals 7. And the first thing says, solve this graphically. So we're going to put these in y1 and y2. So I'm going to grab our graphing calculator. We're going to clear out what's in y1 and y2. In y1, I'm going to put in the absolute value of x squared minus 9. And in y2, I'm going to put in 7. And I'm just going to graph these. What I'm going to notice, I get almost what looks like a W shape. And I actually have 4 points of intersection. 1, 2, 3, 4. So if I quickly sketch that, essentially what this looks like is it looks like this. We have a line at, whoops, that's not right. We have a line at 7, and we have 4 points of intersection here. Now, if we use the intersect feature on our calculator, if we go second function trace, choose number 5 for intersect, I'm going to move all the way over to the far left-hand side. There we go. Hit enter, 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 and tells me my first point of intersection is -4. Okay. I've actually earlier solved and found all the other points of intersection. So what we're going to find out is that our other points of intersection, these 2 points of intersection here are -1.41 and +1.41, and this point on the far side is +4. So there's all of our solutions. Now, that's graphically we came up with those solutions. Now what we're going to do is we're going to do the same thing, but we're going to do it algebraically. So what we're going to look at is we're going to look at the negative of x squared minus 9 equals 7, and we're going to look at the positive of x squared minus 9 equals 7. So if I distribute the negative, I get negative x squared plus 9 equals 7. If I subtract 9 from each side, I'm going to get negative x squared equals -2. If I divide each of these by -1, I get x squared equals 2. And if I take the square root, something you need to remember when you take the square root is that you need to take the positive and negative square root. So x is positive negative root 2, which if I convert that to a decimal is positive and negative 1.41. Just take the square root of 2 and it'll give you 1.41. Now if I solve this, I get x squared minus 9 equals 7. If I add 9 to the other side, I get x squared equals 16. If I take the square root of 16, I get positive and -4 as my answers. So my algebraic solutions confirm what I found graphically.